In this video, we are going to study closed set in a topological space, and we will study topology on a set using a closed set. Okay, let me give you the formal definition of closed sets. Formal definition of closed set. So before I give you the definition of closed set, just let me remind you the definition of open set in a topological space. Okay, let's say we have X is a topological space. Is a topological space with topology tau. We have a topological space X with the topology tau. Then a set U is open in X if U is an element of topology tau. So we have seen this definition of open set in a topological space in one of our previous video or in one of our previous lecture. Okay, a set U in a topological space X is called open in X if U is an element of the topology tau. Now here, as I said before, we are going to give a formal definition of closed set. Now let me give you the definition, and then I will give you some example of a closed set. Okay, let's say I have X is a topological space with topology tau. So we have a topological space X with the topology tau. Then a subset, let's call that subset is uppercase A. A subset A of X is said to be closed in if X minus A is open in X. So basically a subset A is said to be closed in a topological space X if the complement of A, which is X minus A, that's the set difference, if the complement of A is open in X. That means if X complement of A, X minus A, is in this topology tau, then the set A is called closed in X. So this is the definition. Now you can see we define the closed set using its complement. A set is called closed in a topological space if its complement is open. Now let me give you a few examples of closed set in a topological space. Now let's say X is a topological space with a topology with topology tau, and by definition of topological space we know that by definition of topology we know that the whole set X and the empty set they are both in the topology tau. That means empty set and the whole set they are open in X. Okay, X is a topological space with the topology tau. Then, like I said earlier, empty set and the whole set they are open in the topology, they are open in X by definition of topology, because both of them are in topology tau, and they are also closed in this topological space X. Then both empty set and the whole set X are closed, because let's say if empty set is closed, then its complement, it should be open in X. Now let's take the complement of empty set phi. That means X minus empty set phi. If we take the X minus empty set, that's gonna be X. So the complement of empty set is X, and we know that X is in topology tau, so X is open. That means the complement of empty set is open. And X, we have said that X is also closed. So if X is closed, then its complement X minus X, which is empty set, it has to be open in X, and we know that empty set is an element of the topology tau, so this guy is also open in tau. So both complement of empty set, this one, and then complement of the whole set, both complements are open in X, so that empty set and the whole sets are closed in X, because are open in X. Okay, so that's the first example. So if you take a topological space, then the empty subset of that topological space and the whole topological space, they are both open and closed. So in topological space, or in topology, you can have a set which is both closed and open. Let me give you the next example. Let's say we have X, our topological space is the set of real number with a standard topology, and we know that the standard topology is same as the order topology. Okay, let's say X is the set of real number with the standard topology. Then this type of interval AB, that means this type of interval in real number, that means all the real numbers between A and B, including A and B, it's closed. It's closed. This is because if it is closed, then its complement, it must be open. Okay, let's take a look the complement of that closed set AB in R. So this complement, this is the complement of the closed set AB. So if we take a look this complement on the real number system, or in the real line, this is our real line. We have center 0 here. Let's say this, or just let me write down instead of this one, just let me take this is our A B. That's the interval we have taken, and we are saying that this is the closed. If it is closed, then its complement, it has to be open. Now if you take the complement of this guy, and if you take the complement of this interval, then the complement is gonna be this part and the union of this part. Now here this part is from negative infinity to A, and then open or parenthesis here. This A is not included, because A is included here in the bracket. And then also you take the complement, this part, which is B to infinity, and then you take the union of them. Then now here we have just seen that the complement of this interval is the union of this open interval and that open interval. And we know that in topological space, arbitrary unions of open sets or arbitrary unions of open interval is open. So the complement of this interval is the union of two open set is open. It's being a union is being a union of two open intervals negative infinity to a and b to positive infinity. Okay, so so from this example, we have seen that if you have any interval in this form, then that's gonna be closed interval or closed set in R if we consider R with the standard or order topology. That means if you have the interval of like this 0 to 1, then that's gonna be closed set in set of real number with the topology standard topology or order topology. Okay, so that is the another important example of closed set. Now let me give you the third example. Let's say I have X is a topological space, X is a topological space with discrete topology, tau. So discrete topology tau, that means tau is the collection of all the subset of X. So basically discrete topology is the power set of X. So here every subset of X is open in discrete topology because each subset of X is an element of tau. So that's what we already know. Now we can here since every subset of X in discrete topology is open set, then also we can say that every subset is closed in the discrete topology because we know that by definition a set is closed in X or subset of X is closed in X if its complement is open. Since every subset of X is open, and we are saying that every subset of X is also closed in discrete topology because if we take the complement of a subset of X, that's gonna be the union of the remaining subset of X, which is the union of the open subset of X. So if you have the union of open subset of X, then that's gonna be open in topology. So that means the complement of each subset of X in discrete topology is the open set is being the union of it's being the arbitrary union of open set. Okay, so every set is closed or every subset of X is closed because its complement is the union of open sets, and we know that in topology union of open set is open. So since the complement of a set in topological space is the union of the open sets, that's why every set is closed in discrete topology. So that means every set in discrete topology is both open and closed. This is also an important example of closed set. Now let me give you one more example, then we're done with the example. Let's say X is the set of real number with standard topology or with order topology. In fact, standard topology and order topology, they are both same. Now let's take y, which is the union of this interval and that one. Let's say this union uh, with subspace topology. Subspace topology. That means this y, which is the union of those two interval, it's a subspace of R, and we have taken standard topology on R. So basically we have this guy here. This, let's say this is the real line, and we have positive infinity, negative infinity here. That's my center 0. So my y is the union of this interval 0 to 1, and then the union of this interval 2 to 3. Okay, now here we are taking the union of these two interval with the subspace topology. Okay, all right, now here those two intervals, the first one 0 to 1, this interval, it's gonna be open in subspace topology. It's going to be open in y in subspace topology. This is because we know that the element in the subspace topology, each element in the subspace topology, they are going to be the intersection of y with an open interval in the standard topology. Now here we are saying that each of these two intervals, they are open in subspace topology because we can write down this 0 1 as the intersection of y. So here if we take the intersection of this union with the, let's say this one is let's say this one is -1 and that one is let me take this one, it's 1.5. Now if we take the union of this open interval, -1 to positive 1.5, then that is a basis element in the standard topology or in the order topology. And here that means this guy is if it is basis element, then obviously it is an open set or is an element in the standard topology. Now this is the open set in the standard topology because it is the basis element. Now if we take the intersection of this guy with y, and you can see from here, if we take the intersection of this one with this y, then obviously we're going to get this interval. So we have written this interval as the intersection of y with the open set in the standard topology. That means this guy, by definition of subspace topology, this guy is open. Okay, this interval is open in the subspace topology, or it's open in subspace topology. Similarly, we can conclude that the other interval in y, which is 2, 3, we can written down this guy as the intersection of y and. So now let's say we can, okay, now here we can write down this second interval 2 to 3 as the intersection of this interval. Let's say it is 1.5 and that one is, let me call this is 4. Then obviously the interval from 1.4 to 4, this open interval is a open set in the standard topology. And if we take the intersection of this open set with y, then we're gonna get this interval of 2 to 3. So this is 1.5 to 4, and as I said before, this guy is the open set in the standard topology. So we are taking the intersection of y with the open set. Then by definition of subspace topology, this guy is an element of the subspace topology. That means 2, 3 is is open in the subspace topology. Is in the subspace topology. All right, now here let's take the intersection. Now in this Y, each set they are open in the subspace topology. Now if we take the complement of first guy, that's gonna be the second one. That means the complement of 0 1, that is the this interval 2 to 3, which is open. So the complement of this guy is open. That means this interval is closed. Similarly, the complement of 2 3, this interval 2 3 in Y, the complement of this guy in Y is the other interval, and we have just seen that the other interval is open. So by definition, this interval is also closed. So here both interval, this first one and the second one, both are closed in Y. So now here we can write down now both interval. So the complement of 0 1 in Y, that's gonna be 2 3, which implies that 0 1 it's closed, in Y, and also the complement of 2 3, which is the other interval 0 1, and we have seen that 0 1 is open, so that means the complement of 2 3 is open. So this implies that the interval 2 3 is closed in Y, in subspace topology. We are not talking about in the standard topology, we are talking about subspace topology in Y. And the 2 3 is open. We know that 2 3 is open in the standard topology, but in subspace topology in Y 2 3, this interval is closed. All right, so these are the some example of closed set. Okay, now here, so if you remember, in our previous videos, or in previous lecture, we defined the topology using the open set. And now also we can define the topology using the closed set instead of open set. So how to define the topology using the closed set? For that we need a theorem. So let me state this theorem, and then using this theorem we're gonna define, or we're going to study the topology using the closed set. Okay, here's the statement of this theorem. Let's say X is a topological space. Then the following statements are true in topological space X. Then the following conditions hold in X. That means there are three conditions. They are going to be true in topological space, and one of them is empty set and the whole set X are closed, which we have already seen in the example. If you look at the first example, since empty set is the complement of a whole set and the whole set is the complement of empty set, so both are closed, which we have already seen. And the second condition is arbitrary intersections of closed sets are closed. So this condition is also going to be true in a topological space. If you take the arbitrary intersection of the closed sets, that's gonna be closed. We know that in a topological space, arbitrary union of open set is open, but in terms of the closed set, arbitrary intersection, not the union, arbitrary intersection of closed sets are closed. And the third one is finite unions finite unions of closed sets are closed. And we have seen in topology, finite intersection of open sets are open, but in terms of the closed set, finite union, not the intersection, finite unions of closed sets are closed. Let's prove this theorem. So the first condition, we have already seen in first example, both empty sets and the closed sets are closed in the topological space. So first condition is already checked. In the second one, it says the arbitrary intersection of the closed sets are closed in X. So to prove this condition, let's consider a collection. Let's consider a collection of closed sets. Let's consider a collection of closed set A alphas, where alpha is is the index from the index set J. So we have taken the collection of the closed set in X, and we want to show that their intersection is closed. So, and we want to show that union of, not union, I'm sorry, the intersection, their intersection alpha and J is closed. That's what we want here. Okay, so if you want this intersection is closed, then by definition the complement of this intersection, it has to be open. Okay, let's take the complement of this intersection. So the complement of this intersection is this one, and if you use the De Morgan's law, it tells you that that's gonna be union of this complement. Okay, so here you take the complement of each A alpha with X and then take their union. That's gonna be same as you first take the intersection and then take complement. So this one is by De Morgan's law. De Morgan's law. If you are not familiar with De Morgan's law, please you can find the De Morgan's law in the fundamental of mathematics book. Okay, now here we know that A alphas, these A alphas, they are closed set. So that means X minus A alpha, these are the open set by definition of the closed set. And since each A X minus A alpha is open, and since we are in topological space, the arbitrary union of open set is open. So the right side is open set. That means the left side is also open. Okay, now let me just write down that one here. So where the right side, which is union of X minus A alphas in J, it's open. It's being the union. It's being the union of open sets in X. Thus, we can say that intersection of A alpha is in J, is closed. So we just prove that the arbitrary intersection of closed set is closed. And the third one is it says the finite union of closed set is closed. And to prove that one, let's consider the finite closed set in X. Let's say A1 up to AN are closed sets in X, and we want to prove that their union let me write down the union of those n set is like this. We want this one is closed in X. Okay, so if you want to prove this one is closed in X, we need to prove that the intersection of this union is open. Now let's take a look the complement of this union. So again we're going to use De Morgan's law. So De Morgan's law, it tells us that, so if you take the complement of each AI and then take their intersection, okay, so that intersection is going to be same as you first take their union and then take the complement, so that's gonna be the same thing. So it's this one is again by De Morgan's law. Now we know that each AI they are closed, that means this guy X minus AI is open, and we know that in topological space finite intersection of open set is open, so the right side is open, and that means left side is also open, which means the complement of their union is open, so we can say that this union is closed set. So where the intersection of I1 up to n x minus ai is open, it's being a finite intersection, as being a finite intersection of open set, as being a finite intersection of the open set, thus union I1 up to n ai is closed. Okay, now here we have just proved those three conditions in a topological space. The first one, empty sets and the whole sets are closed, arbitrary intersection of closed sets are closed, finite union of closed sets are closed. These three conditions are true. Now we can say that if you have the collection of the closed set in if you have the collection of the closed subset of the given set, and if that collection satisfies these three property, then we can say that that collection is a topology. So that means we can use closed set to study topology in a given set. All right, now here, so we just studied the closed set in a given topological space. Now we're going to discuss closed set in a subspace. Okay, let's say X is a topological space. X is a topological space. X is a topological space, and Y is a subspace of X. Then here is the definition of closed set in a subspace. Then a set A is closed in Y if A is a subset of Y and Y minus A is open in subspace topology of Y. So X is a topological space and Y is a subspace of this topological space, and the set A is closed in this subspace Y if A is the subset of Y and the complement of A with respect to Y is open, or if Y minus A is in subspace topology, then A is called the closed set in a subspace topology. The definition is something similar to the closed set in the topological space, but we have to find that complement with respect to the subspace Y. Okay, uh, so this is the definition of a closed set in topological in subspace. Now our next theorem, I'm going to give you a theorem without a proof, so that theorem will give us more convenient way to check whether the given set in a subspace is closed or not. Let's say X is a topological space, and Y is a subspace. Then A is closed. In Y if and only if we can write down A as an intersection of B and Y, where B is closed in X. So if we can write down A as the intersection of Y and the closed subset of X, then A is closed in Y. And since this is if and only if condition, that means you have both side implication. If A is closed in Y, then we can write down A as the intersection of the closed set in X with Y. And also, if you can write down A as an intersection of closed set in X with Y, then A is going to be closed in Y. So I'm not going to give the proof of this theorem. If you are interested in proof, you can take a look from Munker's book. Okay, all right. Now let me give you one example of a closed set using this definition. Okay, let's say X is a set of real number, or our topological space is the set of real number with the standard topology. It's the standard topology, and let's take Y is this set, this interval 0 1 with subspace topology. Okay, now here what we have is we have this real line. This is center, this is negative infinity, that one is positive infinity, and our subspace of R is this interval 0 to 2. Okay, this is our interval. All right, now here according to this theorem, so let's say I have 1 here. Let me take the intersection of Y with this interval, -1 to 1. So we already know that this type of the interval, they are closed in the standard topology on R, or they are closed in the order topology in R. So we have seen that before. If you look at, I think that was the let me see which example. I think that was the second example. So second example of closed set, we have seen that this kind of the interval, they are closed set in R with the standard topology or the order topology. This is my Y. So here what I'm doing is I'm taking the intersection of this guy, intersection of Y with this interval is -1 to 1. So if I take this intersection, then I have this part. The intersection part is this one. So basically this is going to be this interval 0 to 1. So by this theorem, so here this interval is the intersection of the closed set in X with Y. So by this theorem we can say that this interval is closed in Y in subspace topology. But obviously this is the half open, so it's not closed in the standard topology. This interval is the half open interval, so it is not, but it is not closed in R. So here what we so from this example what we have seen is, you may have a set which is open in the subspace topology, or which is open in subspace but it may not be, sorry. So we have seen here, you may have a set which is closed in subspace, but it may not be closed in the the bigger topological space. So this example, it tells us that you can have a set which is closed in the subspace, but it may not be closed in the is in a bigger topological space. So if you want a set which is closed in subspace and also in the bigger topological space, then there is a criteria that should meet by this subspace. Then we can say that a closed set in subspace is also going to be closed in a topological space. So let me give you that criteria is a theorem. So I'm not going to prove this theorem. If you are interested in the proof, you can take a look in Munker's book. So this theorem, it tells you what is that criteria which makes sure that if you have a closed set in subspace, that's also going to be closed in a bigger topological space. So the criteria is, let Y be a subspace, let Y be a subspace of X, and if A is closed in Y and Y is closed in X, then A is also closed in X. So this theorem, it tells you that if you have a closed set in Y and if the subspace Y itself is the closed in X, then we can say that A is also closed in X. So this is the criteria that A should meet in order to be a closed set in Y, also closed in the bigger topological space.